Hey everyone, welcome back. I hope you all had a great weekend. And today we're going to be getting into section 2.3 from the book. So this section is called Getting Information from the Graph of a Function. And the reason that we might want to do this is because a lot of the times the graph of the function is easier to obtain information from rather than like the algebraic representation of a function, which can sometimes be like it's always more abstract rather than like visual. So you're having to solve for stuff rather than just look at it and interpret it. So that's why we're gonna be looking at graphs. So the first thing is about the values and the domain and range of the function. So if we have a graph, then the height of the graph at a certain x value is called the value. So the height of the graph at a certain x value is the value of the function at that x value. And I mean by value, it's like we mean y value or f of x value. So like the value of the function. So it would be like if we had a graph that looked like this. All right, so each of these marks is like one integer, so like 1, 2, 3, 4, and 1, 2, 3, 4. So this is the graph of f, and when we're talking about values, what we mean to say is that the value of f at -4, which we write as f of -4, of being like these parentheses right here. So f of -4, the value of f at -4 is 1, because when we look at -4, that x value, we are trying to see like, all right, what is the height of this graph? And if I know this graph's not drawn perfectly, but it's supposed to be at 1. So f of -4 is 1. If we wanted f of -1, we'd look at this part of the graph, and it looks like it's 2. And we could, like, f of 0 is clearly 1. F of 3 looks like it's 3. And f of 4 looks like it's 4, and so on. So yeah, those are what values are. We just say like, we write it like this, f of an x value, f of x. And that's like what like a rule. So like if we have a rule, an algebraic expression for the function, then we know to like plug in x. Like this one would be piecewise defined, but we'd know, all right, we need to like plug in x to something over here to get the value. And then for domain, the domain is the set of all x values for which f is defined. And we've gone over the concept of a domain a couple times up until this point, so you guys should be comfortable with that by now. It's just everything that you can legally plug in to the function. But specifically for functions, what you'll see a lot of the time is that it'll only say that the function is defined on a certain interval. So like if we looked at this one, technically, well, so if I drew a point right here and said, all right, this is the entire graph of f, then that means that this function is only defined from -4 to 4. So the domain wouldn't be all real numbers just because there's no like 1 over 0 or square root of a negative. It would at most be just all the x's from -4 to 4 because that's the only thing that the function's defined on. So domain's the set of x values that can be plugged into f essentially, and the range is the corresponding y values for the function on its domain. So the range can only be, so the range is like all possible outputs of the function, and those outputs are only possible if the input was possible. So you have to restrict the range to be only outputs that are from the domain of the function. So here's an example. So like I was saying before, we could have a function that looks like this, where it's like this is supposed to be f of x equals x squared, but it's explicitly said it's defined on negative, like x in between -2 and 2. So the domain, we still have to make sure like nothing in this -2 and 2, like we don't have any issues, but we can see just clearly by looking at the graph that for each of x value in between those two, -2 and 2, we get a value for the function, and only one value. So it is a function, and its domain is that whole thing, but only that, because that's the only place our function is defined on. And then the range would be all possible outputs. So just by looking at the graph, you can see I get every possible output from 0 to 4. Everything in between gets covered. 4 because like this endpoint, f of 2 would be 4. So the range is everything between 0 and 4. Those are all like possible outputs of f. And then in comparison, we could have the function f of x equals x squared defined everywhere. So since this function is defined everywhere and we don't have any problems with like a 1 over 0 or a square root of a negative or something like that, then the domain is all real numbers. But the range, we can see that we never get anything negative as an output, but we can infer from this graph that since it goes on forever, upwards and to the right and upwards to the left, that we do get every output bigger than 0. So the range is going to be y is bigger than or equal to 0. And then I actually messed up this range. We always say y values, so that x should have been a y. The y was between 0 and 4. Alright, and now we can move into talking about solving stuff graphically, equations and inequalities. Graphically. So we do this by comparing function values on certain points and intervals. And so what I mean by that is graphical solutions look like this. So graphical solutions we'll talk about the solutions to two types of things. We have equalities. If I have one function equaling another function, or one function less than another. And the less than or equal to, I'm just going to talk about less than, but the equal to is very similar. So if we have two functions equaling each other, then the solution to that, well, so we have two functions and we want to say, what's the solution to f equals g? So let's say f looks like this, and g looks like this. So we have g of x and f of x. And we want to know when are they equal. Well, what that means is when are the outputs equal for the same x input. So the solution is where they intersect, because that's where the graphs of the functions are equal. The values of those x inputs are equal. So where they intersect. And if this was a and this is b, then the solution is x equals a and b. They could intersect in more places, but this is just in general just a function that intersect, or two functions that intersect in two places. They could intersect 0 places, 1 place, or any number of places, but what's important is that the solution to a function equaling another is where they intersect. And then so if I have the same f and g, and I'm asking when is f of x less than g of x? So just like before, a and b. So this is the graph of f. The graph of f is this one right here. So it's less than g, which is this graph. To the left of a, right, this is f and this is g. So f of x is less than g of x when x is less than a, because when it equals a, they equal each other. So, right, we want it when it's strictly less than. So it's when x is less than a, and then in between a and b, g is bigger. So we don't want that. We want, or sorry, f is bigger from a to b, and then we want f to be smaller. So it looks like and x bigger than b. So that's when f of x is less than g of x. You just kind of look at the graphs and say, all right, when is the graph of one lower than the graph of the other one? And then you just write those intervals, and then you're done. So an example, let's say I had this inequality, x squared plus 1 is less than or equal to negative x squared plus 3. So one thing I can do is graph these as two separate functions. I can graph x plus 1, which looks like this, and then negative x squared plus 3, which looks like this. And then I'm asking when is the first one, which was this, x squared plus 1, and this was negative x squared plus 3. So when is x squared plus 1 less than or equal to that? And so when the graph is lower, looks like from here to here is when x squared plus 1 is less than or equal to the other one. So if we had the information, which is true about these functions, that they intersect at -1 and 1, then what we'd see is that the solution to this inequality is all of the x's in between and including -1 and 1. And then the other way we can do it is just by simply rearranging this equation that we see at the beginning into something with 0 on the other side. So this one would be 2x squared minus 2 is less than or equal to 0. And then I can also just graph this function, which looks like this. That was a little sloppy. It's just steeper than a normal parabola because of this 2 in the front. And what you end up finding is that these x-intercepts are -1 and 1. And the question was asking, when is this graph less than or equal to 0? So just like before, the solution is everything between -1 and 1. So equivalent ways of doing the problem. The second one might be a little bit easier just because then we can really find out where those x-intercepts are using our techniques from last week. All right. Now talk about increasing and decreasing functions. So increasing, decreasing is just a adjective for either an entire function or just a part of a function, just to say, all right, one of these two things is true. So we say f is increasing on an interval if f of x1 is less than f of x2 for every x1 less than x2 in the interval. So what this is saying is if I have two inputs, the inputs being x1 and x2, and x1 is the smaller input, then the output f of x1 better be smaller than f of x2. That's what increasing means. So it's like I have an x1 and an x2, and then the values of that, I have the value of the function being right there, and then the value of x2 being right there. So what it looks like is that the function is going up and to the right. When you're scanning from left to right, the function is going up. That's kind of the conceptual version of increasing. It's while scanning the graph of your function from left to right, is the function going up or down? And then likewise, f is decreasing on an interval if f of x1 is bigger than f of x2 for every x1 smaller than x2 in the interval. So if I had x1 and x2, x1 being the smaller one, then f being decreasing means that this value over there was bigger than this value there. So it's, what it looks like is that f is going down and to the right. So when scanning from left to right, f is going down. What these definitions are for every x1, x2 in the interval. So it's not just because there's 2 points such that this is true. It has to be true for every. So if I chose this x1 again, and then an x2 right here, it better be that this one is lower, and the function didn't do something like this, and just tricked you that it was decreasing. Yeah, so the entire time on that interval, it has to be going down in order for it to be decreasing. So here, I'll just show you the obvious pictures. So increasing, decreasing. So this is just on a certain interval, an increasing function. You start the interval and it's just going up the entire time, never going down. And then decreasing, you start and it would just be going down the entire time, never going up. It could be like curved down like that or that, but like it's never going up and then down. Like it's just going down the entire time or going up the entire time on that interval. That's when we say f is increasing or decreasing on the interval. All right, so quick little example. The function x squared, which we know looks like this. So when is the function going down when scanning from left to right? So if we're scanning this way, it looks like it is going down all the way on this left side of the y-axis. Is going down the whole time until it gets to 0. So it's a decreasing over here and then likewise increasing over here. And this is all x is less than 0, or less than or equal to, because we can include 0 on each of these intervals and it'll still be true. So increasing x is bigger than or equal to 0. So the answer when we would say where is f increasing and decreasing, f is increasing on the interval from minus infinity to 0, including 0. It's decreasing on, oh, I had that backwards, increasing from 0 to infinity, decreasing from negative infinity to 0. And this is the same thing as just saying x is bigger than or equal to 0, x is less than or equal to 0. So either one of those is acceptable answers. You don't have to write final answers in interval notation if you don't want to, but make sure it's either describing it like kind of how you would with set builder notation, or it's in interval notation. All right, and then another example, more complicated one. So say I have something that looks like this. Oh. So that's 2, that's 3. All right. So first note that the function f is defined only from -4 to 3. So like this isn't like one of those functions that goes out to forever. So this is the only part of the function we're looking at. So it's increasing. Let's see, where is the function increasing? Where is it going up? So from -4 to -2, it's going down, and then it's going up from -2, keep still going up all the way to 2. So it's increasing on the closed interval -2 to 2. So this is interval notation, and the closed bracket means include the endpoint rather than the open bracket meaning don't include the endpoint. So it's increasing on that interval, decreasing on that first interval from -4 to -2, and from 2 to 3. It's also decreasing. And so like, just so you guys know, -2 to 2, this interval right there is the same thing as writing this. And then these two, it's the same thing as writing like x in between -4 and -2, or in between 2 and 3. So you can like write, the only reason I was bringing this up is that you can write them like this too. You don't have to write these interval notations. You can write it like this. All right, and then the last little part is about local minimum and maximum values of functions. So a local minimum or maximum is an output of a function. So it would be like an f of a. We'd call it a local maximum value of the function if that value, that specific value, f of a, is bigger than or equal to every f of x whenever x is near a. And likewise, we say f of a is a local minimum value if that value f of a is less than or equal to f of x whenever x is near a. And just to be explicit, what we mean by x being near a means we need to have an interval of x's around a which satisfy these things. So like x near a just means that there's some interval where I can say, all right, for every x in this interval, like that inequality that we had is true, that like the f of a is either bigger than all the f of x's, like bigger than or equal to, or it's less than or equal to. So what this looks like graphically, which is the only way we're going to be talking about local max and mins, you're going to have to graph the function and then figure out if it's like a local max or not. So if I had this function, this big crazy function, it's a function because it passes the vertical line test, but we definitely don't have like a nice way of algebraically writing this. But we can still like look and see where the local maxes and the local mins. So first of all, at this point, since we have the function being defined from like, let's say from 0 to 10, that's where the function is defined, then x equals 0 is a local min, because I can do like this interval, which contains that point, and yeah, it's true that like the value of this input is less than or equal to all the values of like all of the outputs for everything in that interval. So that's what the definition of a local min is. So this point right here is definitely a local min. This point is a local max. Since it's bigger than everything around it, we can look at like this interval right here, and it's clearly bigger than all the outputs of that interval. And so like that's a local min, that's a local max, that's a min, and min, that's a max. So the endpoints are always going to be local maxes or local mins, unless it's a flat function. Like if you had the constant function, like f equals 1, it's just this function at 1, that has no local mins or local maxes, because no matter what interval you choose around a certain value, well, actually, I guess technically based on our definition, every point would be a local min and a local max, because it would be equal to the values of everything around it. And since we let it be less than or equal to, then based on our definition for the constant function, everything would be a local min and a local max. There's a little brain bender. So what I wanted to get to is on this graph, like this point isn't a local max or a local min, because like for this interval around it, or for any interval for that matter, around that point, you have points that are bigger than it and less than it. The reason it worked for the endpoints and we could do that interval is because there are no f's there are no x's to the left of it that are even defined for f, so that counts as a local min because all the points in the domain that are near it satisfy. Alright, so yeah, the gist of it is that local mins on the graph clearly look like a little low point, and the local max is like a high point. Alright, so the problems for 2.3 are these. 7, 9, 15, 23, 31, 33, 43, 45, and 55. Alright, I have office hours tomorrow from 1 to 2, and if you have any questions, stop by or just reach out and email me. Alright, thank you for your attention.